Hello, this is Sanat. Today I will be presenting our work on multitask multi-stage temporal convolution networks for joint recognition of surgical phases and steps in gastric bypass procedures. In this work, we target surgical workflow analysis, that is, reliable recognition of the surgical activities. Surgical workflow analysis plays an important role in the operating room by providing the semantic information required to design clinical decision support systems, training and skill assessment, video indexing, and report generation. To achieve this, a surgical workflow can be decomposed into activities at different levels of granularity, such as procedure, phase, stage, step, and action. In this work, we focus our attention on recognizing phase and step. Previous work in surgical workflow analysis from surgical videos focused on two types of surgical procedures, cholecystectomy and cataract. In terms of surgical activities, phase and tool, and most recently, action triplets. Initial works made use of handcrafted features to extract spatial information from images extracted from videos, and most recently, CNNs have been employed to do the same. In terms of temporal modeling, many works have explored utilizing Hidamako models, recurrent neural networks, and most recently, temporal convolutional networks to extract temporal information available in surgical videos. Our work focuses on another type of surgical procedure, that is gastric bypass. We target joint phase and step recognition. We make use of CNNs to extract spatial information and TCNs to extract the temporal information. The contribution of our work is of twofold. First, we propose a multi-level surgical activity annotation, that is phase and step, for laparoscopic Roux-En-Y gastric bypass procedure. And second, we propose a multitask, multi-stage temporal convolutional network to model jointly both phase and step recognition. Laparoscopic Roux-En-Y gastric bypass procedure is a complex procedure where the stomach is first reduced to create a smaller gastric pouch, the jejunum is separated from the duodenum, and finally the jejunum is directly connected to the newly created smaller gastric pouch. Gastric bypass is a procedure for obesity which is considered a global epidemic by WHO, with approximately 500,000 operations performed every year. In this procedure, we define a phase as a set of fundamental surgical aims to accomplish in order to successfully complete the surgical procedure. A step is defined as a set of surgical actions to perform in order to accomplish a surgical phase. LRYGB procedures are complex and challenging procedure where the duration of a procedure has a mean of 1 hour 50 minutes with a standard deviation of 30 minutes. The whole surgical workflow can be decomposed into 11 phases and 44 steps. The list of all these phases along with the corresponding steps can be seen in the image. For example, P2 here is a phase which corresponds to gastric pouch creation, which consists of crural dissection, hexagon dissection, horizontal stapling, retrogastric dissection, and so on. To analyze this procedure, we construct a dataset of laparoscopic Roux-En-Y gastric bypass procedure consisting of 40 videos which are fully annotated with 11 phases and 44 steps. We split the dataset into 24, 6, and 10 videos for train, validation, and test set respectively. To emphasize the challenges of this procedure, we present here the average duration of all the phases and steps. We see here that the classes are highly imbalanced for both phase and step. We propose an online activity recognition pipeline consisting of two steps. First, we train a feature extraction backend consisting of ResNet50 to recognize both phase and step. Next, we stack the features from the backend along time and train a multi-stage temporal convolution network to recognize jointly both phase and step. To effectively evaluate our method, we compare our method to various baseline models. On the left are all the baseline models which are trained in a single task setup for either phase or step recognition. On the right are all the models which are trained jointly for phase and step recognition in a multitask setup. In the first row, we see all the models which make use of only spatial information for the task of phase or step recognition. In the second row are all the models which consist of a CNN backend followed by an LSTM for temporal modeling. And the last row are all the models which make use of a temporal convolution network for the task of phase or step recognition. To train all the models, we compute the total loss as sum of individual losses for phase and step recognition. We make use of class-weighted cross-entropy loss to compute the individual loss for phase and step. To compute the class weight, we make use of medium frequency balancing. We perform fourfold cross-validation and present our results in terms of accuracy, precision, recall, and FN score. Here, we present our results for the task of face recognition. The first block here represents all the models which does not make use of any temporal convolution networks. We compare our multitask, multistage TCN method to the state-of-the-art techno which was proposed for a single task of face recognition. Here, we see that our method outperforms previous state-of-the-art techno. Here, we present our results for the task of step recognition. Once again, we notice that our method outperforms the state-of-the-art techno for the task of step recognition. To effectively evaluate the capacity of the models for jointly recognizing both phase and step, we compute phase-step accuracy, which is the accuracy of the model to predict both phase and step correctly at a given timestamp. We see that our model again outperforms the previous state-of-the-art techno. We attribute this performance gain for the multitask setup of our model. Here, we present the phase predictions of various models on 3 best and 3 worst videos. Notice that our method is able to capture the smaller phases and also their transitions quite well. Here we see that our model is capturing both P3 and P4 quite well compared to other methods and also the phase transitions. Similarly, we present step predictions of various models on 1 best and 1 worst video. Again, we notice that our model is able to capture smaller steps and their transitions quite well. For example, here we see that our model is capturing both the steps corresponding to green and red quite well. Once again, we see another example where our model performs quite well in recognizing 2 steps highlighted in purple and brown. Interestingly, brown has not been captured by any of the other models. In conclusion, we present multi-level activities for laparoscopic Roux-En-Y gastric bypass procedure, that is phase and step. We present multitask, multi-stage temporal convolution networks for joint phase-step recognition. We show that MTMS-TCN improves performance for both activities and joint recognition. We also verify that TCNs performs better than LSTMs for temporal modeling. Thank you for listening, and we'd also like to thank our funders.